Hi everyone, in this video I'm going to go over section 3.1, so we are now into chapter 3. Chapter 3 is all about taking derivatives but using shortcuts. So in chapter 2 we basically got the underlying foundation, the reasoning, the concept behind derivatives, which I've already mentioned is the biggest part of the course. So that section is absolutely important. Please do not forget it. So a lot of times when we get to chapter 3, we do all these calculations and mechanics and people kind of forget like what we're actually doing, what a derivative actually is. And then when we get to the end of chapter 3 and chapter 4, we have to start applying them and people have to kind of make that adjustment again from going to mechanics and applications. So with the derivative shortcuts, we'll find that there are actually quicker ways to take derivatives. The tricky part about these is deciding what to use and when. So usually once you decide, for example, we use the power rule in this section. Once you decide, I need to use the power rule, it's not too bad to go through it. You'll do it so many times that it's natural. It's not really something that you memorize. It's something that you practice so much that you get more comfortable with. When it gets difficult is when we have all of these different techniques and you have to decide what you need to use and when. So that's definitely going to be the challenging part. I think that you'll like section 3.1. It'll save you a lot of algebra. So here, algebra is still very important, but we're moving away from the really, really heavy algebra we are doing in sections like 2.3, 2.6, 2.7, 2.8. So let's get going with those shortcuts. Some of them I'll introduce briefly and just explain the reasoning behind. I'll do that a lot, and then I'll spend more time working through at least some examples. All right, so in the beginning, so in section 3.1, we're going to be looking at taking the derivative of functions with powers. So we'll talk about this soon, but when we have a variable raised to a constant, of polynomials, and looking at exponential functions. We're also going to look at a couple of rules that are relative to constants. Constants are just numbers. Before we do that, I want to go over a notation. So some of the notation, like the prime notation we've discussed already, denoting the derivative with prime notation is something we've talked about, but I'll write it again. So if I see something like f of x prime, this is the same as f prime of x. This really just means you're taking the derivative of the function f and your independent variable is x. Okay, so this means you're taking the derivative of the function f, and your independent variable is x. So x is your independent variable. All right, there's a different type of notation that we have not introduced yet. This notation is called Leibniz notation. I typed it here. I won't use it as much in the beginning because it tends to be a little bit more difficult for people and I kind of want you to get used to computations, but I'll use it a little bit because it becomes absolutely vital once we get to the more difficult part of this course, which is section 3.9, that's related rates, and also when we talk about implicit differentiation. So it helps you keep track of what is your function, what is your variable. You're going to find that that's really important. So with the Leibniz notation, if I write df dx, here f is really the function, f is my function, okay, and x is the independent variable. All right, you can think, I wrote this down here, but you can think about this like a slope. We know that the change in y, aka y2 minus y1 is on top when we talk about the slope. The change in x is on the bottom, and we should realize at this point that the derivative really is just the slope as a point. So here in this one, if I asked you, what's your function? You should tell me y, because it's on top. And then your independent variable is x. So another way that I could write this is d dx of f. So I'm taking the derivative of the function f with respect to x. So a lot of times we have an actual function to substitute in there. Here we're just generalizing, so we could write it like this. Okay, so we're not going to worry about the Leibniz notation as much, but I am going to put it in there a little bit just so you start getting a little bit comfortable with it. All right, so let's move on to actual derivative properties. Okay, so first thing, when you're taking the derivative of a constant that's all by itself. So really we're asking, okay, well, what is the derivative of a constant? Right, so if we wrote this out in prime notation, we would really be asking if we had some constant c, what is the derivative of c? So that'd be c prime right? The derivative is c of c is 0. I'm going to explain why in a moment. If we wrote this in Leibniz notation, we could say, so or in the Leibniz notation, we could say d dx, okay, of c. So the derivative of c with respect to x, we know c is just a constant, so this is going to be 0. So now the question is, okay, well, why is it true that the derivative of a constant is always 0? We have to remember what the derivative is. So this all goes back to that underlying idea of what is the derivative? Okay, well, we need to recall that the derivative is the slope at a point. Okay, so if I take, or if I think about a function, okay, I'll give an example here. Some y, some x. All right, I know a constant, so let's say y equals some constant. 2 is a constant, some number. Right? I know when I graph that, I really just have some horizontal line. Okay, well, what's the slope of a horizontal line? It's always 0. Therefore, since the slope is always 0 and the derivative is the slope, we know that the derivative must be 0. So I can write this as the graph of a single constant is a horizontal line. That's always true. Okay, the derivative, or else like the slope of a horizontal line is 0. Thus, the derivative is 0. Okay, so big thing to remember first, the derivative of a constant is always 0. At first, these techniques will feel like a lot, but then when you practice with them, you'll say, oh, okay, and it'll just become natural. So I'm going to introduce several things, practice a lot, you'll be okay, especially with these beginning ones. Okay, next scenario. We're taking the derivative, and we have a function multiplied by some constant. All right, so in our prime notation, we would write that as the constant, that's c, times the derivative prime. Right, this is the same thing as c times the derivative. Okay, so essentially, if you have a function multiplied by a constant, you can just factor that constant out and multiply it back in after you take the derivative of the function. I'll explain why in a moment. First, if we want to think about this in Leibniz notation, I'm taking the derivative of c times f of x with respect to x. That's what this part means in words. Okay, again, we can factor the constant out, so I'll factor that out and then eventually multiply it by the derivative of f of x with respect to x. So we can write that as c times df dx, aka c times the derivative. All right, so now if we think, well, why is this true? This one isn't, I mean, I could explain it graphically, but it isn't as easy to explain just by drawing a picture, because depending on what the function f of x is, your picture looks different. In the first one I did, I know that a constant is always just a horizontal line when it's by itself, so I could draw a picture here. Not so easy, so what I'm going to do is think about this algebraically. So all of these derivative shortcuts, all of them, do stem from the definition of a derivative, whether you think about that graphically as the slope at a specific point or analytically using our derivative definition. We always have to keep that definition in mind. Okay, so the reason I'm emphasizing this is because sometimes when people read directions, it'll say calculate the derivative of blank by using the definition of derivatives, and people just start using shortcuts right away. You have to follow the directions there. So this, I'm going to show why it's true by using the definition of a derivative. All right, so I know that. Let's recall the definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so recall that that is the analytical definition of the derivative. All right, now I'm going to use that to establish why this property holds true. All right, so from section 2.7 and 2.8, I know I need to run the x plus h through my original function. Okay, so if I take the derivative of the original function, which is of the form c times f of x, prime. Okay, this is my function. All right, I need to run that through this limit definitions. So h goes to 0. So now I need to plug the x plus h in where I see the x's. Notation is weird, but it's just like what we did before. So I have c times f of, I put an x plus h in here to take care of this part. So I'll do that in purple. Okay, now I have a minus sign from the definition of the derivative right here. Okay, and I have the f of x that I have to keep in there. So here, I know that f of x is just c times f of x. Well, I should say my function is c times f of x. Okay, divide that whole thing by h, again, from the rest of the definition of a derivative. All right, now let's go through our calculations. So here, I'm noting that what I want to eventually show, I use prime notation, so let's scroll up here. I'm trying to show that this is equal to c times f prime of x. Okay, so essentially I want to factor the c out of the top of this, which I can. So I have the limit as h goes to 0 of c times f of x plus h minus f of x all over h. Right, so right here I just factored the c out. Now take note that if I want to, I could write this as c over 1 times this whole fraction. Right, c over 1 is really just c, and I know that when I have a fraction, I multiply across the top and across the bottom. That's the same exact expression that I have. All right, the next thing to remember is by the limit laws, when we have multiplication, we can take the limit of the first multiple and then the limit of the second multiple. So if I take the limit of this first multiple of c, the limit as h goes to 0 of c does not impact that constant at all. There's no h in it. So I know that that's just equal to c, meaning I can take it out or put it in. The limit's not going to impact it. So I can factor that out of the limit because I know the limit does not impact it at all. Then I'm left with the limit as h goes to 0 of f of x plus h minus f of x over h, and it's like magic because by substitution I know that this is the definition of a derivative. Okay, we know, we should remember that the definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. Therefore, we have shown that it is true, and once you prove it, you know you can keep using it. So hopefully that makes sense. It's a little analytical, but I think it's good to see the reasoning behind and what's going on with that. Okay, next scenario. Don't worry, I will show you how to use all these. We'll do examples too. But next scenario is what we call the power rule for differentiation. Okay, the key thing to remember with the power rule is it's of the form x to the n, where n is some constant. All right, I like to think of this as a variable. All right, x is a variable raised to a constant. All right, so when I see variable raised to the constant, that clues me in. I'm going to use the power rule. All right, so usually when I introduce the power rule in class, I actually make the students go through a whole activity. So I'll say, all right, take the derivative of x to the first power using the longhand definition. So I have to go through the limit as h goes to 0 of x plus h minus f of x over h. And I say, okay, do it for x squared. And they're like, oh, really? And I'll say, do it for x cubed. And then I'll say, do it for x to the 100th. And they'll go, oh, I'm not going to do that. And I'll say, all right, well, you better find a pattern, find something that works. And so what I'm going to do is just quickly establish the pattern for the power rule. What I hope that you see is that if we didn't have a derivative technique, it would be a huge pain in the butt. So the reason we have these shortcut techniques is because people in our past, think the brilliant mathematicians of our past, recognize these patterns and realize, you know what, why don't I just use the shortcut and prove that it's true for everything, so then we can use it no matter what instead of having to write things over and over again. So one thing to keep in mind when you're going through these techniques, especially as they get harder, is in your head, and this happened to me when I was in calc, it's like, oh my goodness, this is hard, it's hard to tell like what to do and when. Imagine being the person that has to like think of all this stuff to begin with and then prove that it's true for everybody else to use. and then go through all the calculations as well. So sure, it's tough for us, but there were very, very brilliant people who led up to this, so we should be thankful for that and thankful that we don't have to do that at least. Okay, so anyway, continuing on, like I said, usually this is an activity in class. I'll just show you what that looks like. So usually I say, okay, take the derivative of f of x equals x using the longhand derivative technique. So people will go through, use definition of the derivative. That's what I have here. Okay, they'd have to run the x plus h through the x. That's how we get that part. Carry the minus sign from the definition. And then our function is x, so you just substitute that in. And then once you subtract the x's, you get h over h, which is just 1. Okay, so this is really the same thing as 1 times x to the 0, because x to the 0 is just 1, anything to the 0 power is 1. All right, then we did the same thing for x squared. So take the x plus h, plug it in, so you get x plus h squared minus x squared over h. We do some simplification here, and we end up getting 2x. Note that that is to the first power. Right, do it again for x cubed. When you go through the whole process, I'm sparing you the algebra right now, you get 3x squared. And then when we keep going, I'll say, x to the 4th, what's that? And then they can check, it's 4x cubed. How about x to the 5th? They can check, it's 5x to the 4th. And then when I say, all right, x to the 100th, they're like, no, I'm done, I don't want to do this anymore. And then we're super motivated to get the power rule. Okay, so looking at the pattern we have right here, notice that okay, the x here is to the first power. That 1 ended up in front. Okay, 1 minus 1 gives us the 0 here. Coming to the second part. We started with an x squared. Now we can see that 2 is in front and 2 minus 1 is 1 up here. Okay, x cubed, we see 3 is in front, and then we have 3 minus 1, which is 2. That's now in the exponent. That pattern follows all the way through. So the key thing to remember is, and this is only true if you have a variable raised to a power, is that the power rule tells us that this exponent drops down in front, then you multiply it by the variable raised to the n minus 1. So it is a rule, works every time, but don't forget that this is a proved reason, and it really does stem from that definition of a derivative. So keep in mind, it all stems from this particular definition. Okay, so let's do a couple of basic examples with the power rule, and then I'll move on to some more difficult things. Okay, so let's consider f of x equals 2x to the 4th. Calculate f prime of x. Okay, when I'm going through this, I say, okay, well, I have f prime of x. That's what I'm calculating. All right, the first thing I notice is I have 2. Well, 2 is a constant multiple, so from the constant multiple rule that we talked about above, I can just pull that out in front and then take my derivative of x to the 4th. So now if I focus on x to the 4th, I notice that I have a variable raised to a constant. This means that the power rule applies. So my variable drops down, my constant drops down. So I have 4 times my variable x to the 4 minus 1, right? 2 times 4 is 8, so that gives me 8x to the 3rd, and I am done taking that derivative. All right, let's try another one. All right, this time, let's say we have w of t equals 6 plus pi times t to the 1/3. We'll calculate dw dt. So the way that I would denote that with the Leibniz notation is I'm taking the derivative d of 6 plus pi times t to the 1/3 with respect to t. This is just saying t is your independent variable. Okay, so the derivative d of all this, my function, with respect to t. Okay, so here sometimes students will get confused and they're like, wait a second, what can I use on this? Well, don't let the 6 plus pi confuse you. This really is a constant. Okay, 6 is a constant, pi is a constant. If you add two constants together, you still get a constant. So again, I have a constant multiple. I'm going to rewrite that out in front. Now I need to take the derivative of t to the 1/3. So the exponent will drop down, which gives me 1/3 times my variable t, and that's raised to the 1/3 minus 1. Okay, I want to simplify, meaning write that a little bit nicer. So I have 6 plus pi times I could put that over 3, or I could write times 1/3. That's personal preference. I'm not picky about that. Okay, so times 1/3 t. Right, now 1/3 minus 1 is the same thing as 1/3 minus 3 over 3, so that's a negative 2/3. Okay, so something I want you to keep in mind when you do this is the book is going to be, and especially the website, is going to be extra particular on how you write things and how you simplify. So if you are doing a skills check or an exam, I would be okay with leaving your answers like this. What the book is going to require you to do, and I'm not even going to write all this because it's so algebraically heavy, is they're going to make you write all of your constants together. So 6 plus pi over 3 is the same thing as this. Then you have to drop this part into the denominator since you have a negative exponent. Doesn't end here though. Then you have a root. You end up having a root down here, so they make you rationalize the denominator, simplify it completely, and that's going to be your answer. So the reason I'm telling you this is because if you are someone who likes to do the WebAssign, go for it. I don't care. That's totally fine. However, it is probably going to force you to simplify these every single time. It's going to take you a lot more time. All right, if you like to do the book work, it's going to be faster because usually I say it's not really necessary to simplify unless you have to take a second derivative, because if you do that and you have something big and messy, you don't want to take a second derivative of that. Or if you have to apply it, and that's again because if you have something big and messy and then you have to apply it, it's difficult to work with. So in my opinion, simplifying is something that is necessary and good to do if you have to keep reusing it. But if you're just examining the skill of taking the derivative, it's not really necessary, though you do have to be careful with notation. So do what you want with your homework, but keep in mind the WebAssign will take you longer. If you want to check your answers in the back of the book, but you don't want to simplify, one method that you could use is just plug a number into your answer, plug a number into the answer into the back of the book. If they're the same, your work is probably fine. If you're feeling really unsure, uncomfortable, then you can post on the discussion board and say, hey, this is what I got. I didn't simplify fully. Is this right? Or you could come to open office hours, which nobody has utilized yet, and you can ask me to take a quick peek, and I don't mind doing that at all. Okay, so let's move back along. What I said verbally is summarized right here, so that's good. And let's see. Okay, last little part of this piece of notes, I'll do the exponential property separately, just so you can kind of take a little break in between videos. But the last thing is the sum and difference property for taking derivatives. So what this says here is if you have two functions added and you want to take the derivative of them, you can take the derivative of them separately and then add, and the same concept goes for subtraction. Okay, if we're thinking about y, again, remember these all stem from the definition of a derivative. So in this work, I did a full proof on why this is true for addition. Subtraction looks very similar, so I did type both. So you can follow it through, but essentially I run x plus h through this function, through this part I'm taking the derivative of, that's that part, minus, and then I distribute the negative, you can see it up here, through the f of x and the g. I go through, simplify all the way, and once I do that, you see you get the definition of a derivative here, so f prime of x, the definition of a derivative here, so g prime of x. Therefore, I've shown that if you take the derivative of two things added, two functions added, you can take the derivative separately and then add it back together. So you can explore that more, but I don't want to take up too much time with it. I want to give you a little summary of what we talked about so far, do a couple more examples, and then I'll end this video and record one more for this section. Okay, so thinking of our properties so far, really good to keep track of them because there are going to be a bunch. So what we have is the derivative of a single lone constant is always 0. Okay, if you have a constant multiplied by a function, you can factor it out and then you can multiply it back in as soon as you've taken the derivative. Okay, if you have a variable raised to a constant, then you can drop the variable down in front and raise the variable to, drop the constant down in front, raise the variable to the constant minus 1. That's technically called the power rule. And then finally, you can take the derivative over addition and subtraction separately and then combine back together. All right, so let's utilize those rules, do a couple more examples, and we will be done with this video. However, I will say when you do the homework, okay, they're gonna throw algebra tricks at you. They're gonna make you simplify a little bit so you can use the power rule. You'll have to practice with that, ask questions, just be on your toes about those little algebraic simplifications they make you do at the beginning. Okay, so let's consider f of x equals m times x plus b, where m and b are constant. Find df dx, okay? This is in Leibniz notation. I'll do it in Leibniz notation and prime notation just so you can see both. So if I use Leibniz, I'm going to take the derivative of my function, which I see is mx plus b. And then I know I'm treating x as my variable, so that's why we have the x down here. All right, by the summation property, I can take the derivative of these individually. So I have dmx dx, okay, the derivative of the first function, plus the derivative d of b with respect to x. All right, m is a constant multiple, so I can factor that out. Okay, and b, we see b right here is just a constant. The derivative of any constant is 0, so that's 0. So now I have m times, okay, the derivative of x with respect to x. So keep in mind, x is to the first power. I have a variable raised to a constant. This means that the power rule applies. So I have 1 times x to the 0. This is really just equal to m times 1, which is m. Okay, so should that make sense? Yeah, it should, right? If you take the slope of a linear equation, we should probably all remember that the slope is always just the value in front of an x. So it makes sense that we would get 1 for there. All right, let's try another one. Oh wait, sorry, prime notation. So if you did this in prime notation, you'd write well, you could just write f prime of x actually. Say f prime of x is equivalent to mx, oh boy, mx prime plus b prime. Okay, the derivative of mx we did over here. We found that's just m. The derivative of b, so prime notation, not a 1, is 0. So we get the same thing. Okay, either notation is fine. Eventually you'll have to get used to Leibniz, but if you like the prime notation better, go for it, use that. Okay, so next one, we have z of w is 3w squared minus w cubed. We want to calculate the derivative of z and treat w as the independent variable. All right, so first one, 3 is a constant multiple. Therefore, just bring it out in front. Okay, for w squared, I have a variable raised to a constant, which tells me that I can use the power rule. So the 2 is going to drop down. I have 1. Okay, and the exponent 2 minus 1 is just 1, so I'm not going to write anything there. Okay, I know by the sum and difference rule, I can just take the derivative of w cubed separate. So I have minus, take the derivative here. Using the power rule, we get 3w squared. All right, so eventually I'm going to do this all at once, and you'll be able to too without showing all the steps, but I did show this intermediate step here. Okay, so 3 times 2 is 6. Therefore, for our final answer, we have 6w minus 3w squared. So these give you an idea of what they look like all combined. Like I said, there will be more algebra. For a quick example, let's say we have like f of x is equal to x to the 4th minus 3x to the 1/3 over x squared. All right, so this, it's like, oh my gosh, that looks really tricky. It's division. If you remember how to simplify, the power rule works for all of them. So here, this is equal to x to the 4th over x squared minus 3x to the 1/3 over x squared. Common denominator, so you can split it. Doing algebra right now, not doing any calculus right now. X to the 4th over x squared is equal to x squared. That's by exponential rules. Okay, so 4 minus 2 is 2. Okay, hold the minus sign. We have 3 in the exponent here, but recall from properties of exponents that this is the same thing as x to the 1/3 minus 2, which is really x to the 1/3 minus 6 over 3, so negative 5/3. That means that this would really be 3x to the negative 5/3. All right, so now you have it in the form where you can use the power rule here, you can use the power rule here, you can take the derivative. So the homework will throw stuff like that at you where you kind of have to simplify algebraically before you can use the properties, but take note of it, do your best on it, ask questions as you go, come to office hours, or set up an appointment with me if you'd like.